own Corning, but also a company called, I guess it's called Southern Research.
Southern Research,
yeah,
right.
Which really focused on, he was a VP of that and focused on energy and environmental problems there for a number of years. But now he's the CEO of this organization called RAPID, which is part of the AICHE's involvement with the Department of Energy. And if you've read the announcement, you know what the acronym stands for, but this has a lot to do with the way in which you have intense processes that are pretty energy intensive as well as other things, and making them more efficient and dealing with this at sort of deployment at scale. So it's a great pleasure to have you here, Bill. He did his undergraduate work at Georgia Tech and then came to MIT for his PhD, and I learned today that we're exposing him to weather that he doesn't really like since he was raised in Florida. But on the other hand, he must have gotten used to crummy weather when he was in Cambridge for so many years. But we're glad to have you here, Bill. So
thank you very much. I appreciate it. So it's a pleasure for me to be here. I was reflecting on this earlier. I've been in this part of New York a number of times at Corning and visiting companies, but I've never been to Cornell. So this was it was a great opportunity to come and visit, see the earliest glimpses into the kinds of work going on here, meet some of the students and learn about what you're doing. It will absolutely not be my last trip here. We will be doing more together. So, and thank you again for the kind words. What I'd like to do is talk about RAPID. RAPID, I'll explain who we are and what we do in context in a little bit, but we are in the business, as Jeff said, of trying to transform how the process industries think about process development, how we build and design and deploy equipment, maybe not in that order, I guess design first, then build and deploy. And in the end, we're also in the business of helping train the next generation of engineers, much like Cornell and other universities are, to think differently about these things, this thing we call modular processing and process intensification. So let me say a little bit of, give you a little bit of information about Manufacturing USA and what the manufacturing institutes are. So there are 14 manufacturing institutes in the United States that were created under something called the Ramey Act. It's congressional law focused on driving competitive advantage in U.S. manufacturing with a focus on advanced manufacturing. So thinking about what the next generation of manufacturing and industrialization will look like in the U.S. There are 14. It's a little bit difficult to see on these slides, but the ones that are highlighted in a dark outline, well, somewhere on here I have a, well, we'll see. Maybe not working today. In any event, the ones that are outlined in black or dark blue are funded by Department of Defense. The one that is highlighted in a green outline, NIMBLE, down in the bottom right, is funded through NIST, Department of Commerce. And then the 5 that are highlighted in the kind of orangey yellow color are DOE funded. RAPID, ours, shown in the bottom right, is funded by DOE. We were the 10th of 14 manufacturing institutes. And we were created as a partnership, as Jeff said, between AICHE, the American Institute of Chemical Engineers, and the Department of Energy's Advanced Manufacturing Office. So just by show of hands, how many chemical engineers in the audience? So maybe 25% or so of the group. We, I would say in many ways, are biased somewhat towards the language and the terminology that we all as chemical engineers use. So I'll try to put some of that in context for the folks that might not be as familiar with it. But at the end of the day, RAPID is a $150 million partnership between DOE and American Institute of Chemical Engineers. That's $70 million in funding over 5 years from DOE under a cooperative agreement with the Department of Energy. And then the rest, the other 80+ million, comes from our members. Those members, industry, academia, other nonprofits, government labs, et cetera, put dollars into a pool with the federal dollars to fund projects and do education and workforce development. I'll talk about that in a minute. We are right now sitting at 75 members strong, split a little more heavily weighted towards universities, labs, and nonprofits, but over the last 6 months, we've added almost exclusively companies to the mix. I'm hoping Cornell will be a member of Rapid in the future, and we are adding more and more companies as we go forward. So what do we do? You know, I could talk probably for the next 4 hours about all the nuances of the different things that the manufacturing institutes do and what Rapid does specifically. But the 4 bullets here really capture everything, and they kind of are the outline or the agenda for the talk. We are in the business of building a community. So process intensification, I'll explain what that means in a minute, is a term in our field of work that's been around for 40 or 50 years, but it's gotten a lot more traction in other parts of the world than in the US. So we are in the business of building a community of members, academics, labs, companies, around this idea of process intensification and modularization, and providing the forums to help drive new development in that area. Part of that is thought leadership, so defining the areas in which our members should work, what we should be doing, and where there's greatest advantage for these kinds of new technologies. Providing, well, first building and then providing the educational content that builds on what we all as engineers learn in school, but also what companies need for all of us as engineers to learn to be able to deploy technologies like these in the field. And then the last piece is really where the rubber meets the road. We fund development projects at our member institutions through funding calls. We do multiple calls for projects. We've done 2 so far in the R&D space. We're right now running one in education and workforce development, basically to find really cool problems that need to be solved, have our members come back to us with proposals to solve those. We vet them, we fund them, and then we help monitor and run those projects over time. And I'll talk through all of these over the next few minutes. So just one slide on our member community. You'll see a lot of other universities up there that you recognize. You'll see some of the national labs, SRNL, PNNL are there, and then many companies. Again, we're growing, and I think the interesting point here is, as we look forward, for technologies like anything in the process industry uses to be commercialized and have an impact on the way the process industries operate, companies like ExxonMobil and DuPont and Dow and Praxair and others have to be ready. Well, first they have to be engaged in the projects, and they have to be ready to take these technologies into practice at some point down the road. Having more and more companies in the mix is critical for us. And so my goal would be, if you were to see this slide later this year or this time next year, there will be more companies on it, but also more members overall. So let me say a couple of words about these things called process intensification and process modularization. And I've tried to distill it down to some phrasing, and I have a couple of other slides with examples. So again, for those of us who are chemical engineers, we were generally all trained to think in terms of something called unit operations. So you have a unit operation where you react chemical A and chemical B and you make chemical C and maybe a slew of byproducts. And ideally you want as high a purity product in that as you can get at highest yield and lowest cost, but generally you don't get there in one step. So you have to do separations and heat exchange and other ancillary processes around that reaction, around that transformation, maybe some physical transformations and so forth, to get to the final product that is valuable in the marketplace. That still holds. We were all trained classically this way, and this is the way process development generally works in the process industries. Whether you're in ag or petrochemicals or specialty chemicals or fertilizer manufacturing, it works this way. But there is a paradigm shift that's beginning to happen. And the idea is, if we step back maybe one step or even half a step from unit ops and think about the phenomenological underpinnings of what we're talking about, the chemical transformation, the physical transformation that's going on, maybe we can find novel ways of putting the pieces together differently. So for example, some chemical reactions produce byproducts that cause the reaction, which is inherently reversible, to reach a limit. They're equilibrium limited reactions. And so in those cases, you have to somehow separate that product away from the reactants to allow the reaction to proceed to completion. You might choose to do that in 2 steps. You go up to a certain conversion, so much of your reactant goes to so much product, and then you take it forward, you separate it, and you take the unreacted material and you put it back in and you recycle. Works, can be energy intensive, can be capital intensive, so operating costs and capital costs can be higher. Maybe you put the pieces together in a different way. The little cartoon in the bottom center is depicting a hollow fiber membrane reactor where you run a reaction in the core of that membrane reactor, or maybe on the surface of it, and instantaneously, or nearly so, you take the reactant or a byproduct and you move it away from where the reaction's occurring. And so you transcend that boundary, that equilibrium boundary, and you can drive extent of reaction, you can get higher yield, and even better, you can do your reaction and separation in one step. So you have one piece of equipment with lower capital intensity and lower recycle and lower operating cost than before. Another way of thinking about it is that you might take one operation that today would occur in multiple pieces of equipment. That's the example in the bottom left. You have a feed with multiple components that you want to separate. Most chemical engineers are really familiar with distillation. You do a separation in one column, you make a pure overhead product, you get a bottoms product. It's contaminated or has 2 components in it, so you need a second column or a second separation step to get to the final purity that you need. Another way of looking at this is using something called a dividing wall column. And this is literally taking a distillation column, which is a big stainless steel cylinder with trays or packing or something inside to affect the separation, and putting a vertical wall in it and making this center section and the top and bottom sections behave the way those 2 columns in series would normally behave. Interesting part about this is that single unit, and this is in practice. In fact, the Germans, more than any other, BASF and other companies have put this into practice in a number of different plants. They've managed to do this in a way that it saves capital cost because you need only one heat exchanger at the bottom putting energy in, and you only need one heat exchanger at the top taking the energy back out. The capital cost of the one distillation column, the one piece of equipment, might be a little bit higher, but operating costs and energy costs are generally lower, and product purity can be the same or better in many cases. These are examples of process intensification, and there are hundreds, maybe thousands of different ways that you could put the pieces together. So I would say this piece is, again, it's an extension of traditional chemical engineering fundamentals. Now, I realize there are a lot of folks in the room who are not chemies, who have double E's, maybe mechanical engineers and others. The world of modular processing actually reads on your disciplines almost more strongly than on chemical engineering. So the interesting part about modular processing is, again, we're trained to think in terms of economies of scale. There's, in designing and building equipment, again, in our world, there's something called power law economics. Usually the capital cost of a piece of equipment scales with area or volume at less than 1 to 1, usually scales at an exponent of 0.6 or 0.7, meaning if you build a bigger piece of equipment, it will cost more, but it will cost less per unit pound of output that you produce. It turns out that that's generally true when you're talking about the equipment. When you actually factor in all the design costs and the capital risk and the other things that companies face, and you roll it all in, the costs are often higher than that. And so modular processing offers a different way of thinking about this. So let's say that you want to run a process, and normally your plant is going to be, world scale plant would be the size of this building, or maybe the size of 5 buildings around us. Another way of thinking about it would be to build a skid or a module the size of this room. One module produces 1x the amount of material that you want. The first one of its kind might cost a lot of money, but the 10th or the 100th or the 500th or 1000th of that module should cost a lot less, because now back to the mechanical engineering and industrial engineering side, the hope is that you can produce a skid like that one shown in the picture there in an assembly line factory, rather than as a custom-built piece of equipment that's a one-off. And if we can get there, the unique part about this would be that a manufacturer could earn into scale, earn into capacity, by instead of building one giant plant, they could build 10 of those. And so if they need 1x capacity today and 5x capacity 2 years from now, they can add on modules over time.
So has anyone done like the analysis to show that that is economically viable? Because I'm thinking of a process that I worked on as an undergrad. We were purifying HCl gas and needed quite expensive tantalum. In fact, was the only material that had the chemical characteristics for it. And I'm thinking numbering that up might be too expensive. It might be better to just build one.
So the question for the visual audience is, are there examples of where this has been done, or are there economics that show that this is viable? So we are undertaking a study with the Construction Industry Institute to actually bear this out and look at certain cases where this would apply. This is not applicable in every case, nor is process intensification. They don't apply universally. It's a new tool in the toolbox. So a way to think about this, the example that was given was HCl, hydrochloric acid processing or purification, needing a particularly high value raw material in the manufacturing of the equipment. That's one where building one custom piece of equipment at scale probably does make more sense. The flip side is, if you want to unlock stranded raw materials, for example, biomass. Waste biomass is a great example. It costs a lot to aggregate biomass, collect it, transport it, get it to a central processing facility. So I'm sure a lot of folks in the room have heard about USDA and Department of Energy funding these efforts in building an integrated biorefinery. It's been tried over and over again. It hasn't ever really come to fruition. Part of the problem is, one, you need to get enough biomass in one place, enough of the same type of biomass in one place that you can get predictable operations. It's unlikely to happen. Instead, if you build a module and take it to the field where the raw material is, you can tune that module to match what the biomass is. And natural gas is the same type of raw material. Unlocking stranded natural gas wells. Go ahead.
It's also sometimes the market forecast isn't very accurate. So when you have modular, you can sort of hedge that.
That's exactly right.
Yeah.
So again, the comment was, when market forecasts for a particular product or market segment are off, that can tank an entire project. So I tend to look at that. So look, I've spent most of my career in industry, and I've been on the side of having to decide whether we write a check or make the case for writing a check for building a new process. Building a first-of-a-kind process is really, really risky for companies. And so the way this usually works is, you design it in a lab, you make a bigger sort of bench pilot, something that's maybe kilograms per hour, then you build a pilot plant that's tens or hundreds of kilograms an hour, then you build a demonstration plant that's hundreds or thousands of kilograms an hour, And then maybe, if you're lucky, really lucky, somebody writes a check to build the commercial scale system. And in the kinds of industries that we're talking about, commercial scale is measured in the hundreds of millions to billions of dollars of capital. Demo is in the tens of millions. Pilot is maybe single digit to tens of millions. If you could build that module for $10 or $15 million and take it to the field and have that be your pilot, your demo, and your commercial scale plant, you completely change the game in terms of capital risk and in terms of commercialization. These are the pieces that Rapid is trying to push. So the fundamental connectivity, and if we return to kind of an engineering taxonomy nomenclature way of looking at it, process intensification can be looked at in a couple of ways, right? You have equipment, new tools, new reactor designs, new separators, et cetera, that can be put together in unique ways. Maybe folks in the room have heard about or read about microreactors or microchannel reactors. Small-scale devices with small passages with very efficient heat and mass transfer. These are all tools in the toolbox that allow us to do what we did before, just more efficiently with lower energy penalty. The other way to look at it is not from the equipment standpoint, but phenomenologically or methodologically, if that's a word, changing the method. So putting the pieces together, multifunction in one step, bringing new forcing functions like microwave reaction, putting microwaves into a reactor as opposed to purely thermal heat. So bringing electromagnetic energy, using acoustics or some other technology to get energy into a process to run a reaction or a separation differently than we do today. And these are a constantly growing list of tools. And the classic example again, for the chemies in the room, the classic example of process intensification is reactive distillation. This is an example where all the stuff on the left where it says conventional, that was the conventional process for reacting acetic acid and methanol together to make methyl acetate. And you see that the product is up in the center in one of the center distillation columns. This massive train of equipment was designed to produce that one product. Eastman Chemical, with help from academics and others, developed a reactive distillation process that collapsed all of that down to one distillation column. Very elegant solution. Do it in one step. One piece of equipment, one step. Harder to control for sure, but with better process control technologies, with better computational and modeling techniques that came to pass in the late 80s, early 90s. They could model it, they could pilot it, they could build it, and finally they could control it. This is the kind of thing that we're pushing. So, I mentioned before, we do 4 things, right? We build a community. So we have a community of members. Thought leadership is the second piece of what we do. So when AICHE formed Rapid with the Department of Energy, the first thing we did after they hired the first CEO, not me, there was another person who was the founding CEO, we went out and gathered industry and academic experts from across a range of process industry segments, and we roadmapped out different areas where process intensification and process modularization could have the greatest impact. And we came up with 3 applications verticals and 3 cross-cutting fundamentals. And so I think of this as the application verticals are the industry practice areas where all that stuff that I just showed you on those last couple of slides could be put into practice and have the greatest impact. Chemical and commodity processing is things like converting components of, let's say, alkanes like ethane or propane to alkenes, ethylene and propylene, which are some of the highest volume commodity chemicals used. Those processes consume an incredible amount of energy in the global scale processes that use them. if we can demonstrate a way of looking at those processes or doing those processes differently that save 1 or 2 or 10% energy, it's quadrillions of BTUs of energy that could be saved on a global scale if this is put into practice. Huge impact with very tiny incremental savings on one process. Natural gas upgrading. So today you hear a lot about natural gas fracking. Basically unlocking reserves of natural gas in areas that are inherently more stranded. So western Pennsylvania, western New York, eastern Ohio. The new natural gas economy that has been created in this country based on natural gas fracking has changed the chemical industry really dramatically here. But having said that, there are a lot of natural gas wells that aren't economical because they're stranded. They produce natural gas that's either low quality, it's sour, it has too much sulfur in it and can't be processed, or it's really not economical to put it in a truck to get it to a plant somewhere and turn it into something more valuable. We're looking at, again, how do you take that modular concept, put it at or near the wellhead, and then make natural gas into something, or a component that's coming up with the natural gas, for example, ethane or propane. How do you turn that into something much more valuable that then can tolerate the transport cost? We talked a little bit about renewable bioproducts. Getting water out or managing water in the bioprocess industry. We think of that today as stranded biomass, pulp and paper, et cetera, but we've been talking a lot about ag, food and beverage, and the waste materials and the water usage that come along with that. A lot of application for the technologies that we're pushing. And then the cross-cutting fundamentals are things that underpin all of these verticals. So it turns out that if you were to go into modeling software that exists today, I don't know what Cornell uses, Aspen Plus or ChemStation's tools, to model out a process, there aren't modules that can describe, meaning modules, not the kind of modules I'm talking about. There aren't tools within that simulation software to describe these process intensified systems. So we're funding projects to develop that, to develop the blocks that go into Aspen Plus, so that the next generation of engineers, maybe not any of us sitting in this room now, but 5 years from now or 10 years from now, the next generation of these tools will be able to describe all of these processes. Intensified process fundamentals, the first one there is really this idea of introducing new forcing functions. So acoustics, microwaves, et cetera. And then the last one on the far end is module manufacturing. So I alluded to this before. For the electrical engineers, the mechanical engineers, the industrial engineers, this is about bringing entirely new fabrication techniques to bear. And I'll tell a story. So I'll foreshadow a little bit. One of the projects that I'll highlight later is one that's run out of University of Pittsburgh with Lubrizol, the specialty chemicals company. I won't say the details of that, but we were in one of Pitt's facilities looking at their additive manufacturing capability. And they had designed and 3D printed a heat exchanger. So it was a heat exchanger about the size of this water bottle sitting here that could realistically be, if it was designed right, the reactor for this system that they're developing. So imagine that you go from a chemical plant that's the size of maybe 3 of these rooms to a reactor that could sit in your hand and that's printed on demand. That's a pretty different world than the one we all grew up in and that you're all sort of being trained in now. That's what we're trying to fund in that last piece. I want to talk for just a couple of minutes about the education piece. So, and I bring this up because for the students in the room, there is content that Rapid has available today where you can go online and learn all about what we're talking about. You can learn it for free. So with that road mapping that I just showed around the technology, we went out and asked our industry and academic colleagues what was needed in terms of pedagogy and curriculum. And we developed a body of knowledge. This is actually a document that details out all of the heat transfer and mass transfer and reaction engineering and separations fundamentals that need to be created to ultimately build coursework in process intensification. We have that codified, and we are in the process of funding other university partners as well as developing on our own e-learning content and face-to-face courses that will allow all of us to go take these classes somewhere and learn about this stuff that I'm talking about. We run webinars, we have, again, face-to-face courses, we have an internship program, and I want to highlight a couple of these just so that you're aware. I would be more than happy to share this. I think the slides will be available. You can find all this information online, but our CTO, who just left, rotated to go back to ExxonMobil, Jim Bielenberg, built this e-learning course. It's a 4-hour course. It has tests along the way, and we're also developing an accreditation program. It's not ready yet, but later this year there will be a certificate program where when students or engineers in practice go through that, we will have an accreditation program in process intensification. Like project management professionals, we want to create process intensification professionals. But this is a fundamentals of process intensification course where you can learn in much more detail that I can provide in 40 minutes all this stuff that I'm talking about at a high level. We are in the process of developing heat transfer, mass transfer, separations, reaction engineering fundamentals courses that apply to this, design for PI, modeling for PI courses. So again, it's somewhat early days, one course, 11 available webinars that our members, our experts put together to describe things like microreactors, oscillatory flow reactors, thinking about module manufacturing. All of this is available. Again, members, student members of the American Institute of Chemical Engineers can go on through our portal and access this. Anybody who's a non-member can access it, but there's a fee. And of course, even non-members can join AICHE. We would welcome any engineers to come be part of the mix. Students join for free.
Yeah, exactly. Very inexpensive.
Yeah, it's
It can't be cheaper than that.
it's there is no reason why a student engineer should not be a member of our organization. And then the last piece that I want to highlight, because this reads directly on all of you. Last summer, we had the idea of running a pilot program in interning. So internships, co-ops, et cetera, exist at different companies. Different universities have different philosophies about how to get students into industry. At the end of the day, we put together an intern program. We hoped for 4 interns. We had 15. We right now have, so it was well oversubscribed. It was a huge success. Rapid members are offering up internship opportunities to students, graduate and undergraduate, who are working on or could work on PI or modular processing technologies. And we're pretty broad in terms of how we define that. So right now we have 7 interns in our spring program that runs through April. Nominations will open soon for summer. Actually, they sort of rolling nominations. For the faculty in the audience, if you want to nominate, please do. Certainly, if you wanted to have a student here at Cornell doing it, Cornell would have to be a member at that point, but hopefully we'll get there. This is going to be a continuous process, and what's unique about our internship program, it's not just the work experience. We provide course content, process safety, leadership training, and technical training. All the stuff I just showed you, the students get along the way. So it's a really nice perk for our rapid members, I would say. So look, I think I have, about 15 minutes left, give or take? We're supposed to wrap about 10 after?
Yeah, I think good to leave a few minutes for questions.
I will.
So,
So I want to spend the balance of the time highlighting a couple of projects. I have more slides than I'll cover, but I just want to say this. I mentioned we have these 6 focus areas. So those are the ones highlighted there. By project count, we have 32 research projects that we are funding that our member companies are doing. So to be clear, while we are the Rapid Manufacturing Institute, we don't run the projects and do the research. I pay organizations like yours to do work that's relevant. We have a proposal process that we do. We've done 2 calls for proposals, one in 17 and one in 18. We'll do another later this year. And our projects on average are 2 to 4 years. They're small to quite large. Typically, they're heavily cost shared, meaning that the people proposing it put a lot of skin in the game. They bring dollars or equipment or time to bear. And the point of the pie charts is to show you that we're pretty well distributed across the 6 focus areas. So I think what I'll do, let me spend maybe 4 minutes here highlighting, I want to highlight 3 projects. I have 6 or 7, but I want to highlight a couple. I mentioned before this microreactor thing, the printed reactor. So Lubrizol, the chemical company, generally does processes in batch, meaning they have a big reactor, they put all the products in, they react them for a certain amount of time, then they take them out and purify them, or they are at the purity where they're used. These are additives for performance chemicals, the oil industry. They make products that go into Mobil 1 and Haviland and other motor oils and things. So they have this, the chemistry that's shown in the slide there, they do today in this batch reactor. Well, University of Pittsburgh is working with them to do this continuously. And so they are at a point now where they've proven this in the laboratory. They're getting ready to build a pilot plant, but it turns out that the pilot plant is actually going to become the commercial plant. It's a skid about the size of the podium and the table adjacent to it that will produce all of the capacity that they need on an annual basis for that product. Today, they produce it by campaigning it. They produce a lot for a period of time, they put it in a warehouse, it becomes inventory, and it sits on the shelf until the customer buys it. The beauty of this new process, they can produce it just in time. They don't need inventory. And this process, this modular reactor, might run 10% of the time for one product, 10% of the time for another product. They produce it just in time, ships to the customer, and they're done. No inventory. And another beautiful part of it is, it's 90% lower capital cost to build that thing than to build what they used before. Capital cost savings, energy consumption is down, which by the way is one of our big metrics for DOE. It's a modular system. It could be deployed where the raw materials are, or it could be deployed even at a customer location. Really elegant solution. Let me talk about this one. So this is a project that University of Delaware and Rutgers are doing. Jeff, this is one I was mentioning to you earlier. Really interesting technology. So most of us think about sugar as a raw material, either as a food source or as a raw material for fermentation, for making wine or beer, or ethanol for fuel or other things like that, industrial alcohols. Well, it turns out you can take glucose and convert it to dimethylfuran, that middle compound that's shown in the green block, and then do a subsequent conversion to the commodity chemical paraxylene. The interesting part is the first reaction runs in water with a catalyst. So you react the glucose in water and you make that middle compound. The second reaction runs in the oil phase. So these guys have come up with this elegant solution that's shown down here in the bottom. In a tube reactor, they have water droplets, and then they have those water droplets surrounded by an oil phase. And so literally, this is in a 1/4-inch tube. You see water flowing through as droplets, surrounded by an oil phase. The first reaction occurs at very fast reaction rates in the water. The DMF, the middle compound, selectively partitions across the interface of that droplet into the oil, and then reacts to make the paraxylene. And this is all done continuously. It can be made modular. It can be done in a way, I mean, it's incredibly elegant engineering built on well-defined and well-known chemistry, but with new catalysts and new materials developed in it. So this is a case where they're predicting based on the existing process, I think a 25 or 30% energy reduction, energy cost reduction. It can be modularized, and it could easily be back to our bioproducts and distributed raw materials perspective. We actually have another project that I'm not highlighting that's looking at unlocking sugars from biomass using a non-traditional modular mechanism. You marry that with this, you could be making paraxylene in a distributed way in part of the country that has lots of ag waste, whereas before you were making it only on the Gulf Coast where you had heavy petrochemical refineries. You reduce the transportation cost of the paraxylene, you use a waste material to make sugar, you use the sugar to do something much more valuable than making ethanol. And by the way, you don't have lots of water to deal with the way you do in most fermentation processes. Very elegant solutions. Let me talk about this one and then I'll stop. So I mentioned before forcing functions. So it turns out that we have this project that's Shell, Pitt, West Virginia University, and NETL in Morgantown, where they are looking at doing effectively methane activation and methane conversion to, let's say, C2 compounds like acetylene or ethylene, or ultimately to aromatic compounds like benzene. This is really hard chemistry to do. It's hard to get a methane molecule to activate in a way that it wants to add to itself and grow as a chain versus just being converted to carbon in one case on the catalyst, or to convert to CO2 or carbon monoxide. So they have a unique catalyst that's designed on a surface. They run it in a microwave reactor. So rather than just putting heat in by conduction, they're activating the catalyst at a certain frequency of microwave radiation that they see a dramatic spike in selectivity and a dramatic spike in conversion. So their yields are much higher than they would see under other conditions. And by the way, if you were to do this thermally, this chemistry only occurs at, I think it's 625 to 650 degrees C. They can do it with a bulk temperature of more like 400 to 425 with microwave reaction. The question, of course, is at the catalyst site, is the temperature really as high as it was before? We don't know that. Fundamentals, process, energy savings, and again, a potentially elegant solution, but very, very early in its life cycle. So like I said before, I could talk for hours about the projects. These were 3. There are 29 other ones that touch on modeling and simulation and all the other areas. But let me stop. What questions do you have?
Thank you for I told you it was going to be different. So there's got to be, I'm sure a few of you are excited about this. You can see the opportunities in some areas that were.
Please.
So I'm very interested in the second project, converting glucose to DMF.
Mm-hmm.
I wonder what is the conversion rate and how long does it take, and the selectivity of the reaction and all the specs.
Yeah, we can turn the lights on. Sure.
So the question was about this project, the sugars to bioproducts. What's the conversion, selectivity, et cetera? I will tell you off the top of my head, I don't have them top of mind. I can easily share those data with you. So let's be in touch independently and I can share that information to the extent that the project team is able and ready to share it as well.
We'll be involved with some of the biomass talks that we have later too. So.
And you know, what we're interested in doing is engaging broadly around applications. So I mentioned before, Iowa State has a project where they're pyrolyzing biomass, and instead of making, I mean, it's an autothermal process, so it generates enough energy to keep going, but instead of making a fuel product, they're making a phenolic oil and free sugar. you marry that free sugar up with a process like this, and it's a nice process put together. So if there are other technologies that you think could be combined with this, let us know.
Yeah, Osman, thank you very much for coming. So I'm a soil scientist. I'm not a chemie. So I'm
He's
very
the
much
biochar
interested in
expert, I think.
Okay, sure.
What are some of the business models for these modular things? What's the blueprint for that? Because obviously then there will be not one big owner of a factory, but there will be many owners, or is this a franchise, or is this a lease program? Will every farmer have something like that, or is it owned centrally, similar to a digestion system in Europe?
So,
Cooperative type.
yeah, so the question is, what's the business model associated with commercialization? And I'll hedge a little bit and say it depends really strongly on the project, because we have 32 projects. Full disclosure, Rapid owns no intellectual property on this. The project teams own and negotiate their own independent intellectual property rights. So if Robert Brown at Iowa State, developing this autothermal pyrolyzer, decides that he wants to put it into a company and commercialize it, I have no say over that. So the business model piece is decided if it's commercialized at the project team level. So that's the real answer. I'll give you my philosophical answer. I think from a modular processing standpoint, the only way it's going to work is when you tie a particular market need. So come back to, I showed this example, the graphic in the bottom right, the picture of that modular system is a sour gas purification unit that integrates a really unique catalyst and heat and mass transfer system developed by a small company. They are going to be a leasing model to wellhead operators. So they'll lease it. The wellhead operator basically pays on a per unit purified natural gas output out of that unit. And their company installs it, operates it, and gets a perpetuity payment based on that.
So before we go to the last question or so, I just want to remind you that we are going to have this kind of informal discussion over lunch down at in 128, just down the hall here. And I know that we have some openings, I think, from what I heard earlier. I don't know whether that's true now, but I'd really encourage you guys to come and continue this. Let's take one last question, Bill, and then we'll adjourn to a more informal Q&A.
Absolutely. Any more? No last takers?
We're waiting for lunch, right?
Yeah, I'm standing between you and food, so
Well,
thank you again for the time.